When a distributed system operates under heavy load, a single bottleneck rarely stays isolated. It triggers a cascade. Nodes misfire, timeouts stack up, and what starts as a localized network blip spreads into a system-wide blackout. To prevent this, engineers implement Apache Kafka. It serves as the industry standard for high-throughput event streaming, trusted to process trillions of messages without losing a single byte of data. But out of the box, Kafka's default guarantees are dangerously insufficient. Its baseline protocol promises at least once delivery and guarantees chronological ordering only within a single partition. Relying on these default settings in a production environment leads directly to silent data corruption. Downstream microservices execute duplicate events, double charging customers for a single transaction, or they process ghost orders that never actually committed to your primary database. Kafka provides a highly durable append-only log. But end-to-end reliability requires explicit, fault-tolerant architectural patterns built around the broker. Trusting Kafka's default behavior without an architectural lopper is an engineering liability. To guarantee consistency across services, we have to rebuild the ingestion, routing, and consumption layers from scratch. The first failure point occurs before data even reaches the broker. When an application writes to a database and then publishes an event to Kafka, it assumes two sequential operations can be coordinated safely without a distributed transaction. This is the dual write problem. Look at this workflow. The application successfully commits a row to the database, but immediately after, the network call to Kafka times out. The application retains a record of the order, but the downstream microservices never receive the event. The order becomes a ghost. Adding application-level retries usually makes the error worse. If the initial Kafka network call succeeded, but the broker's acknowledgement was lost, the retry loop fires a second identical payload. One database insert has now injected duplicate events into the stream. The definitive solution to this race condition is the Transactional Outbox Pattern. We eliminate the second write entirely from the application's critical path. In this architecture, the application never interacts with the Kafka producer. It writes to a relational outbox table. Because this insert executes inside the exact same ACID transaction boundary as the core business logic, the database guarantees that both records are saved, or neither is. To bridge the gap to Kafka asynchronously, we implement Change Data Capture, or CDC. A connector like Debezium continuously tails the database's write-ahead log. When it detects a new row in the outbox table, it streams that exact payload to the MSK cluster. By utilizing the relational database as the sole atomic boundary, the ingestion phase achieves absolute consistency. Application logic is completely decoupled from Kafka network failures. Once the data is safely ingested, the next hurdle is processing it efficiently. Kafka scales throughput horizontally by splitting a single topic across multiple partitions. But Kafka enforces a strict physical limit. It guarantees chronological event ordering only within a single partition. Across different partitions, there is zero coordination. If we distribute messages randomly, related events will scatter across these separate tracks. A downstream shipping service might ingest a shipped event before the payment cleared event arrives, completely breaking the required business logic. To enforce chronological order for related entities, we apply the partition key pattern. When the producer attaches a specific string, like an order ID, to the event, Kafka applies its Murmur2 hashing algorithm. This deterministic math evaluates every packet bearing that exact string and routes them all down one specific sequential partition track. The primary risk here is designing a key with low cardinality. Grouping events by a broad category, like a country code, routes a massive percentage of your traffic to a single broker, creating a hot partition that bottlenecks the entire cluster. Partition key design is a zero-sum calculation. You must balance the requirement for strict chronological sequence against the need to distribute load horizontally across your consumers. Even with perfect chronological ordering, Kafka's default delivery model practically guarantees duplicates. The protocol intentionally prioritizes at least once delivery, repeating a message rather than risking data loss. Observe this consumer timeline. The node ingests a packet and successfully updates a downstream database. But milliseconds before the offset commit reaches the broker, the consumer crashes. The broker never recorded the completion. When the consumer restarts, it pulls that exact same uncommitted packet. processes it again, and executes a second duplicate database update. To prevent this, we have to decouple the state of the business action from Kafka's internal offset tracking. We achieve this with the idempotent consumer pattern, integrating a highly available, low-latency NoSQL store like DynamoDB directly into the processing logic. As the consumer receives a packet, it extracts a unique key, mapping the topic, partition, and offset. It pings the DynamoDB table using an atomic attribute not exists condition. If the database confirms this key has already been processed, the consumer simply drops the duplicate packet. An idempotent architecture doesn't stop duplicates from traveling over the network. It simply renders them mathematically harmless to the business state. Even a perfectly deduplicated stream will encounter errors. A resilient architecture explicitly separates permanent data failures from transient network failures. A permanent failure, or poison pill, is typically an irreconcilable schema mismatch or malformed JSON. No amount of automated retries will make this payload processable. Because Kafka commits offsets sequentially, a consumer that fails to parse this jagged payload will retry it infinitely. A massive backlog of healthy data builds up directly behind it. A single invalid message locks the entire partition. We unblock the pipeline using the dead letter queue pattern. After exhausting its retry limit, the consumer routes the malformed packet into a separate quarantine topic. It then commits the original offset, allowing the healthy packets to finally flow. Transient failures require a different approach. API rate limits and deadlocks resolve on their own if the downstream service is given enough time to recover. Hitting a struggling service with immediate retries only guarantees a second failure. We implement exponential backoff, spacing out the retry attempts logarithmically. But if 1,000 consumers encounter a network blip and execute an identical backoff delay, they create a thundering herd. Synchronized waves of automated retries crash into the recovering service at the exact same millisecond, executing a self-inflicted denial of service attack. The mathematical countermeasure is jitter. By injecting randomized variables into the delay algorithm, we desynchronize the automated retry waves, dispersing the load. Intelligent failure routing isolates localized damage. It prevents a single malformed packet or a temporary database lock from cascading into a total system collapse. We have dismantled Kafka's default behaviors and replaced them with explicit structural controls. This completed architecture traces a single event moving safely through the pipeline. In the ingestion phase, the transactional outbox guarantees absolute consistency between our database and the event stream, eliminating race conditions. During transit, hash partition keys force chronological integrity, keeping related events in sequence. At the consumption layer, idempotent consumers neutralize network duplicates, while dead letter queues gracefully isolate poison pills from the critical path. Apache Kafka is a highly resilient transport layer, but true end-to-end distributed consistency is achieved only by engineering these 5 explicit patterns around it.